Hello everyone, today we're going to be going over the solution to the SI problem set 9 that should be posted in the files on Canvas. If you haven't tried to work through it for yourself yet, I really recommend that you do that first before watching a video going over the solutions, just so you can get practice and see maybe what you did which might not have worked or might have worked in a different way. Okay, but the first problem, this whole problem set is on angular momentum. We're just picking on that today because you've been focusing on it a lot in the lectures, so I thought I dedicated a whole problem set to it. The first one, we're going to be showing that the z component of the angular momentum operator can be expressed in terms of these partial derivatives times the coordinates. This was thrown around a lot in the lectures. Thought I'd make you do it for yourself so you can see where it comes from. And where it comes from is the classical definition of angular momentum, and then we'll make the substitution where derivatives become where momenta becomes partial derivatives. Okay, so we start off by saying that L is equal to the cross product of the position and the momentum. And I had to fight myself from using my way of doing cross products in terms of the Levi-Civita symbol, but just know that that's coming eventually with cross product stuff for you guys. That's in your future. But let's do it the regular way that I think everyone normally learns in terms of these determinants and whatnot. So the cross product we write in terms of this, x hat, y hat, z hat, and then we have the coordinates, so we have x, y, z, and the momentum components, px, py, pz. To find the z component, we cover up the z column and then the row of the basis vectors, and we take the determinant of what's remaining. So it'll be xpy minus ypx. So Lz is equal to xpy minus ypx. The last step of this is to use the substitution, or we quantize momentum in the way that it becomes a derivative. So if we have the ith component of the momentum operator is equal to minus I h bar d, what am I calling it, r, over ri. So if I is 1, that corresponds to x. If I is 2, that corresponds to y, and so on. So p sub x would be minus I h bar d dx. We make this substitution into the two momenta. Both are going to have a common factor of minus I h bar. So this is equal to minus I h bar x d over dy minus y d over dx. And this reproduces the equations that you've been seeing all the time in the lectures. Okay, great. So that's where it comes from. You can do this for each individual component of the angular momentum. A nice little mnemonic that comes out of it. If you think of x, y, z kind of pointing this way where you can turn these. If you turn counterclockwise, that's a cyclic permutation. And if you turn counterclockwise, so x, z, y, that's an anticyclic. So if we look at z, the next one over is going to be an x, and then it's going to be a derivative with respect to y. And then if we go z and we go backwards, then it's going to be minus sign because we're going the other way, and it's going to be minus y d dx. And you can do that for all of the components. You can do that anytime you have a cross product. So that's why when I write down what the different components of the angular momentum are, y and x, it'll look like I just have this stuff memorized, but really I'm just thinking of it in terms of these little permutations. So that's the solution for problem 1. Problem 2 is going to be much more involved, so let's go ahead and erase this and get started. So for this problem I've just started, we're going to be showing that if we act on the wave function with Ly and then on Lx, and subtract from that if we act with x first and then y, we get I h bar times the z component of angular momentum. So that's what we're going to be trying to show today, or for this problem. And to start with that, to expedite the process, I've started by writing out the operators for the different components of angular momentum. So we see z, it goes x, y, y, x. So it's the one that doesn't show up in here. For y, z, x, x, z, and x, y, z, z, y. So it follows the same pattern that I was trying to illustrate previously. So what we want to do is we want to show this, and I'm going to start this by splitting this up into two terms. The reason we have this acting on a wave function to begin with at all is because since these are derivatives, and we have wave functions that are functions of those variables that we're taking derivatives with respect to, if we didn't have it acting on this wave function, we would be losing some of the information. More specifically, we'd be losing terms that would come out of, say, things like product rule and stuff like that. So whenever we want to look at properties of an operator, you always end up having it act on some test function first, just to make sure you have all the information. Then the wave function should end up factoring out at the end, and you can kind of identify terms, these different properties of the operators. But let's go ahead and get started. So I'm going to start by calling this part here just term 1, and this part term 2. And then at the end, we're going to look at equation 1 minus equation 2, just because this is going to blow up a little bit. Okay, so for term 1, we have, and can you see that? You can. Great. So we're going to be looking at Lx, Ly acting on the wave function. So I'm going to be thorough for the first part, then it's going to be the exact same procedure for the next, so I might skip a couple steps for the second one, just because it's the exact same thing. But for this one, we have Lx, which is this guy. We have a minus IH bar. Oops. And then we have the Lx operator, d over dz minus z d over dy. Then we have the other, we have Ly, which also carries a minus IH bar. So I'm just going to pull that out as a square of this. That way I can write it as just the product of these derivative terms. Ly, so we've got a z d over dx minus x d over dz acting on the wave function. So that's one. The first step is to distribute this term here that corresponds to y and have it act on the wave function. So this is equal to minus IH bar squared y d dz minus z d dy. We have z d dx acting on the wave function, so that's just z times the x derivative of the wave function minus x times the z derivative of the wave function. Okay? And now we're doing it again. Now we're going to take derivatives of this. Now this is where you have to be a bit careful, because when we're taking here, we're taking the derivative with respect to z that's being distributed to this term, but z definitely depends on z, and the wave function depends on z. So in order to take this derivative, we have to use product rule. So this is equal to minus IH bar squared. I get that minus I squared is minus 1, but this is going to make things come out nicer in the end so that we don't have to think too much. So this is equal to y d dz of this. Y d dz of z times d psi dx minus, so I'm really just distributing right here, minus y. None of the other terms that we're taking derivatives with respect to, actually let me just keep being thorough. So we have minus y d dz of x d psi dz. Then we have these inner terms, minus z d dy of z d psi dx, and then a plus z d dy of x d psi dz. Okay? So all I did was distribute these terms out. The only one that's actually subject to product rule is the first term, because this is the only one that has a product of two things that depend on z. So this is equal to minus I h bar squared. Oops. When we distribute, so this is, we'll take the derivative of z first, so it's going to give us a y d psi dx plus yz, the second derivative of psi with respect to z with respect to x. one thing to keep in mind before we go any further is partial derivatives that you'll have learned in your calculus courses. It doesn't matter which order you go in. It commutes with each other, we say. That's actually a word that we end up using to describe these differences. But partial derivatives commute. If I go forward and then sideways, that's the same as if I go sideways and then forward. Okay, so we'll be able to move these around later. Okay, so now we have a minus yx d squared psi dz squared minus z squared d squared psi dy dx. And we have a plus zx d squared psi dy dz. So that's equal to equation 1. Okay, now let's do this again. So now we're going to do this for the second term, where instead of xy, it's yx. Okay, so this is equal to, so 2 is equal to, I'm going to write out the first term. So we've got yx, and let's go ahead and do our minus ih bar squareds, minus ih bar squareds, z ddx minus x ddz, and then we're acting on it with lx. So I'm going to go ahead and already just distribute our guy out. So we're just distributing this lx to psi. So all I'm doing is I'm writing a psi here. So times y d psi dz minus z d psi dy. Okay, which is equal to minus ih bar squared. We'll take these derivatives. By looking at this, we see that the only term that's going to be subject to product rule is going to be the last term, because we have a derivative with respect to z and then this product again. So that's the only term that we're going to have to be careful with. Okay, so I'm just going to write out the other ones now. So this is going to be a z y d squared psi dx dz. That's this term. Minus z squared d squared psi dx dy minus xy d squared psi dz squared. And then finally we have the product rule one. So minus signs on both, so it's net positive, plus x d psi dy plus xz d squared psi dz dy. Fantastic. So this is equation 2. And now what we want to do is we want to do equation 1 minus equation 2. So we'll have a common factor of that minus ih bar. So we have 1 minus 2 minus ih bar squared. We'll come back to this term, but here we have a yz dz dx. Here we have a yz dz dx, and we're subtracting the two. So these terms cancel. Next, yx dz squared, yx dz squared. Now these carry the same sign, so when we take the difference, they cancel again. One becomes positive. Z squared dy dx, z squared dy dx, same side, so they cancel when we take the difference. And finally, zx dy dz, and we have a zx dy dz, same sign, so they cancel. So we don't have to write too much, actually. This ends up becoming, we have a y d psi dx that has nothing to cancel with here, so that survives. Minus this x d psi dy. Okay. Now I can actually just factor out this wave function again, and we'll just know that we're applying derivatives to it. So I'll just erase that real quick. I'm just writing this out here. And when we distribute this out, we get the derivative of the wave function. Now the last thing that I'm going to do is I'm going to pull out a minus sign. So this is equal to minus, so we have a minus I h bar times a minus I h bar. And when we pull out the minus, these signs switch. So we have an x d over dy minus y d over dx acting on the wave function. But minus I h bar times this combination, that's just Lz. So this term is just Lz. And then we have a minus times minus I h bar, which is I h bar. So we get that this whole thing is equal to I h bar Lz acting on the wave function. So we've proved what we wanted to prove. Now one thing, just for the sake of conciseness and brevity in the future, oftentimes if we have something like AB minus BA, we shorthand this in the following way, AB. It's called the commutator. So we could write this as the commutator. This would be, you would say this as the commutator of A with B. And we could write this as the commutator of x, Lx and Ly. So, in a nice concise equation, we get that the commutator of Lx and Ly psi is equal to I h bar Lz psi. Or in other words, we can just say that this commutator Lx, Ly is equal to I h bar Lz. And you can derive these commutator relations for any component of these angular momenta. But the interesting takeaway for all of this is we took the difference, we did AB minus BA of these operators acting on the wave function. So in a way you can think of it as saying, let's measure the y component of angular momentum and then the x. And then we'll see how this differs from if we measure x first and then y. Now, in ordinary circumstances, why would that be any different? But the fact that this is not zero, which is what that would mean if it was no different, if I measured this and then I measured this, is that the same as me measuring this and then measuring this? This math that we just went through says in general it doesn't. What that means, the way that you interpret this, is that you cannot make simultaneous measurements of any two components of angular momentum. You can't measure the x and the y component at the same time. Measuring x changes what y would be. So that's the big takeaway of this. Like, people pick on position and momentum, that has the same thing. It has its own non-zero commutator relation, which means that you can't measure position and momentum at the same time. But this is telling us you can't even measure momentum and momentum at the same time in a weird way. So I always found that particularly interesting. And this makes it even more powerful when you can. When you do get AB minus BA equals 0. That means that you can make a simultaneous measurement. One example would be like the angular momentum and the Hamiltonian. If you go through all of this, which is quite a bit longer, you get that you can actually make those measurements at the same time, or the square of the angular momentum and any component. So that's the big punchline here, is in showing this, which just seemed like a whole bunch of abstract math, it has a pretty profound consequence that you can't measure these two things at the same time. So with that being said, this was the hard one, I think, out of the problems that I wrote for you guys. But let's get on to the third one. For the final problem, like, this stuff has all been great theory stuff where we're writing out the actual expressions for how to calculate theoretically what the angular momentum is by defining what the operators look like in a differential form. But now we're going to actually calculate something. So for this problem, I give you the wave function for the three-dimensional harmonic oscillator, and the normalization constant won't contribute, so I'm not writing that out. And I say I want to calculate what the z component of the angular momentum is. So we're suggesting that this wave function, yes, it's an eigenstate to the Hamiltonian, but it should also be an eigenstate to the angular momentum operator. And in other words, that means when I operate on the wave function with the angular momentum operator, I should get back the wave function times a number. And that number ends up being some integer times h bar. the integer will end up depending on the state, the excited state, the energy level of the wave function. So let's go ahead and see, let's go ahead and just brute force our way through this. Let's apply our operator to the wave function and see what we get. This is the ground state for the harmonic oscillator. So in its essence, we're calculating what is the angular momentum of a particle confined to a harmonic oscillator potential in its ground state. That's what we're finding right now. If you're looking at this, you can maybe even tell what the answer is going to be. And this is a direct analogy with Bohr's formulation of angular momentum. He said that it should be some integer multiple of h bar. Let's see if it's right. Only with him, h bar, or the integer, had to start with 1. So let's go ahead and stop talking and start calculating. So Lz acting on the wave function is equal to minus I h bar. I'm also going to call this guy lambda, just so I'm not writing omega over h bars anymore. So we have minus I h bar n x d dy minus y d dx acting on this exponential. Minus lambda x squared plus y squared plus z squared. Okay, when we take the derivative of this Gaussian with respect to any variable, we're going to have to use chain rule. Okay, the derivative of an exponential is an exponential. So that part's easy. So whatever we get, it's going to be equal to minus I h bar n, a bunch of stuff, times the same exponential, because for chain rule, it's the derivative of the outside times the derivative of the inside. So the derivative of an exponential is an exponential. So on the outside, we'll still have an exponential. But when we differentiate the inside, if we differentiate this with respect to y, so we have an x d dy, the derivative of this is going to be a minus 2y times lambda. So this is going to be a minus 2xy lambda. And then similarly, when we differentiate with respect to x, we're going to get the same exponential at the end, and then the derivative of the inside, which is going to be a minus 2x lambda. And we have a minus sign here, so it's going to be a plus 2xy lambda, and then we factor now the exponential that still survives. Okay, so we have the original function times this exponential. So we can write this as minus I h bar, whatever this is, times the original function. So it was, in fact, an eigenstate because we got the function back times a number. But what is the number? We have minus 2xy lambda plus 2xy lambda. That's 0. So we get that Lz acting on the ground state wave function for the harmonic oscillator is equal to 0 times psi of x, y, z. So the harmonic ground state of the harmonic oscillator is an eigenstate to angular momentum in the z direction with an eigenvalue of 0. That's the main takeaway here. And this isn't even unique to the harmonic oscillator. You may think that that's it's a coincidence, but it turns out that this will always happen whenever the potential is spherically symmetric. So when we write down the Schrodinger equation, there's that potential term. If that exhibits a spherical symmetry, the ground state solution to that will have an angular momentum of 0. Always. No exceptions. So that I always found was pretty interesting. But that completes the solution for this week's problem set. Just getting you guys used to working with this operator formalism. It's very different. And getting used to writing these observables as the derivatives and whatnot. Getting used to writing test functions for commutators. This stuff is going to follow you everywhere. But with that being said, I hope you guys found this video helpful. Just shoot me an email if you have any questions that maybe I didn't address in this video. And I'll see you guys there.